Assalamualaikum and salam sejahtera. We are from Group Power Rangers. We are going to present about Lotka-Voltera predictor prey model about rabbit and wolves. So, the Lotka-Voltera model, also known as the predator-prey model, is commonly used to study the dynamics between prey and predator. For this project, we chose rabbits and wolves as the prey and predator. There are a few assumptions that we need to consider in order to use this model. Firstly, the prey population has abundant food at all times. The predator population's food supply is solely dependent on the prey population. The rate of change of population is proportional to its size. The environment is constant and genetic adaptation is insignificant, and predators have boundless appetites. So for our original model, we found two differential equations. The first differential equation defines the rate population of rabbit, and the second defines the rate population of wolf. So for our data, we use wolf-rabbit predator prey simulation data. This is because this population data is very limited and difficult to obtain. Animal predator prey population data are normally collected by experts and animal organizations from controlled experiments. So prey predator population data is not readily available. So for the first differential equation, we modified our equation. We include the natural death rate of rabbit. And nothing is changed for the second differential equation. So for our project, there are 5 coefficients needed. So for the first 4 coefficients, we use A, B, C, and D. We use the data from Kumar 2006. But for the natural death rate of rabbit, we only find the data from mortality rate in rabbits between 4 to 8 weeks of age. Therefore, we use this data that is 12% from Rashwa and Marai 2000. Next, for the equilibrium point, we know at equilibrium for both differential equations must be 0. So by following this step, we can find the equilibrium points for our model. Therefore, our equilibrium points that obtains are 0, 0, 25 over 30, 1250 over 21, and negative 4300 over 147.
So first, the solution for equilibrium point 1, 0, 0, we use the Jacobian matrix and linearization. Because when we substitute the equilibrium point into the Jacobian matrix, and we could see that 1, 0, 0, negative 0.5 is the answer for the matrix. And from the matrix, we used the linearized system, and we got the dn1 over dt equals to n1, meanwhile dn2 over dt equals to negative 0.5 and 2. From this, we use the Laplace transformation into the linearized system, we obtain two equations and using initial values from the data, n1 and 2 equals to 100. And then we obtained that n1s equals to 100 over s minus 1, meanwhile n2s equals to 100 over s plus 0.5. Then we apply the inverse Laplace transformation to both equations and we got n1t equals to 100 e to the power of t, meanwhile n2t equals to 100 e to the power of negative 0.5 t. Next, we used the second method, which is the linear differential equation system using the eigenvalue and vectors. So first, we find the eigenvalues based on the Jacobian matrix, and we got two eigenvalues, which are 1 and negative 0.5. Then, from these eigenvalues, we find the eigenvectors, and then we got x1 equals to 1, 0, x2 equals to 0, 1. Then we substitute both eigenvalue and eigenvector in the equation to obtain the general solution. And then to solve C1 and C2, we use the initial values from the data. And then lastly, we conclude that n1t equals to 100 e to the power of t, meanwhile n2t equals to 100 e to the power of negative 0.5t, which is the same answer using the Laplace transformation as well.
In order to obtain the solution for equilibrium point 225 over 30, we apply linearization using Jacobian matrix, where we substitute the equilibrium point into the Jacobian matrix to obtain the linearized system as follows. The linearized system can be solved using Laplace transformation, where we apply the Laplace transformation to obtain the following equation. And then we use the initial values from the data to obtain the Laplace transformation for n1 and n2. Since n1 is kind of complex, so we can simplify n1 using the partial fractions. Finally, we apply the inverse Laplace transformation to obtain the solutions for n1 and n2, which is n1 equals to 23,200 over 57 exponent negative t minus 70,500 over 57 exponent negative 0.43 t, while n2 equals to 100 exponent negative 0.43 t. The linearized system can also be solved using the linear differential equation system, where at first we find the eigenvalues, then the eigenvectors. Secondly, we substitute both eigenvalues and eigenvectors into the general equation to obtain the general solution as follows. Thirdly, we substitute the initial values from the data to solve for C1 and C2, and we obtain C1 equals to 23,200 over 57 and C2 equals to 100. Finally, we substitute the C1 and C2 into the general solution to obtain the specified solution as follows, which is similar to what we obtained using Laplace transformation just now.
Okay, now I will explain the solution for equilibrium point 3. So we use the Jacobian matrix and we do the linearization process by substituting the equilibrium point 3 into the Jacobian matrix, and we get like this. So that we can form the linearized system. So for the Laplace transformation method, from the linearized system, we apply the Laplace transformation and we get these two equations. So after that, we substitute the initial value, and then we do some rearrangement and we simplify to get n1 and n2 in terms of s, like this. So the details for this calculation, we put it in the report. So after that, we simplify the n1 and n2 using the partial fraction, and we get like this, and we can see there is a pattern here. So after that, we apply the inverse Laplace transformation and we get the solution. So for the second method is the linear differential equation system using the eigenvalue and vector. So from the Jacobian matrix, we find the eigenvalues with this condition and we get the eigenvalues, and after that we find the eigenvector that match the eigenvalue. So after that we substitute the eigenvalue and the eigenvector into the equation to get the general solution. Like this. So after that, to solve for C1 and C2, we must substitute the initial value, and then we can get for the value for C1 and C2. Then after that, we substitute the value to get this specified solution like this. So we observe that both methods give the same solution.
Next, I'm going to present about the solution's behavior and phase flow traits. For the first equilibrium point, the eigenvalues obtained are 1 and negative 0.5, which are two distinct real eigenvalues with opposite signs. And using the determinant of Jacobian matrix, we got negative 0.5, which is less than 0. Hence, a saddle point phase flow trait will be formed and it is unstable. For the second equilibrium point, the eigenvalues obtained are negative 1 and negative 0.43, which are two distinct real eigenvalues with the same negative sign. And using the determinant and trace of Jacobian matrix, the determinant value is in between 0 and 1/4 of 3 squared. So a two tangents phase flow trait will be formed and it is asymptotically stable. For the third equilibrium point, the eigenvalues obtained are 0.406829 and negative 7.549686, which are two distinct real eigenvalues with opposite signs. And using the determinant of Jacobian matrix, it is less than 0. Hence, a saddle point phase flow trait will be formed and it is unstable. So, in conclusion, we obtained 3 equilibrium points, and since the system is not linear, we did a linearization process using Jacobian matrix. And to solve the system, we use 2 methods, which are Laplace transformation and linear differential equation system using eigenvalue and vector. However, for the third equilibrium point N2, the second solution, the equation obtained is slightly different between using Laplace transformation and using eigenvalue. As you can see here, for eigenvalue and vector, it does not have 0.00008. So we conclude that 0.00008 is approximately close to 0 due to inaccuracy of the manual calculations. So in the end, for equilibrium point 1 and 3, we got a saddle point phase flow trait, and for equilibrium point 2, we obtained a two tangents node phase flow trait. Thank you.